John, our Vice President at Intech Automation, is diving deep into the different considerations for needle bending equipment, tooling, and technology to create exact product geometry no matter the requirements. Here is what John will cover. Accommodating geometry detail in angle bends, radius bends, and tip bends. Gauge sizes and how specialty equipment can handle varying lengths. Accommodating existing features like cross-drilled holes or sharp tips with a single bevel cut. Orientation of features and how to clock the position of the angle bend. Equipment to accommodate your requirements at the rate you need. Automating machine tooling. Recipe configuration to automate features in your cannula forming operation. Recipe-specific tooling for more complex radius bends and angle bends. Our process to create prototype tools, soft tooling, to form samples. Inspect and measure to ensure geometry requirements for the hard tooling.
So the considerations for the equipment design to be able to accommodate the variations in raw material coming in, as well as the variations in the desired output from the machine, include the gauge diameter of the needle, the length of the needle, the geometries that need to be imparted into that needle. So you can have, it's common to have angle bends, it's common to have radius bends, it's common to have tip bends, which are very small features. On a cystotome, for example, needle it's got a 0.5 millimeter 90-degree tip bend. That's a very small and precise feature of that device. So you can have a lot of variation in the geometry that is trying to be produced, as well as the variations in the raw material that you're trying to produce those processes to. Gauge sizes can run from 12 gauge up to 30 gauge. Lengths can be whatever they need to be. There's also considerations that many cannula have existing features in them, such as cross-drilled holes or sharp tips that have a single bevel cut. And so in order to perform many of the operations to those types of needles, we need to first understand and capture the orientation of those features. So we need to clock the position of an angle bend with respect to a cross-drilled hole. Or if we're doing a tip bend, for example, we have to ensure that the rotational position of that needle is aligned properly, so that when our tooling comes in and bends the tip, it's bending it in the right plane or the right degree of freedom to produce the desired end result. So those types of systems can incorporate several different technologies depending on what the in-feed raw materials are and what the resulting products coming out the output is. If a machine only needs to do angle bends, for example, and that's all the customer needs to do, we would first understand, okay, what are the angle bends that you need to achieve? Are you going from 45 degrees to 60 degrees? Do you need a 0 to 90 degrees? Do you have any bends that go beyond 90 degrees? What gauge sizes are you trying to accomplish? What lengths are you trying to accomplish? What cycle time or production rates are you trying to accomplish? And we would design the equipment to be able to address all of their requirements at the rate that they need. In this instance, where we're only talking about a simple angle bend, the machine tooling can be much more automated than more complex geometries. So, for example, to accommodate different gauge sizes, we're generally bending these cannula over a male and a female form of a hard tool. And so we can utilize servo actuators to position the hard tools, whether you have a fixed tool and you have a moving tool, and then you have generally a servo that controls the vertical position from up above, where you can control really all three parameters through a recipe configuration through our HMI to be able to produce, I'll say it's not unlimited, but it's a very high number of product SKUs by just changing offset values of those servo positioners. So if you want the tip that you're bending at 45 degrees to be 4 millimeters long instead of 6 millimeters long, you can change the position of that vertical actuator so that when it presents the needle to the forming tools, it doesn't insert at 6 millimeters, it inserts at 4 millimeters. And you can position the fixed tool based on the gauge size. So as the diameter of the cannula changes, the support tool, the fixed tool that you're bending the portion that's being angle bent around, needs to be able to be compensated for the different diameters or the different gauge sizes. So if you're using a small gauge, for example, we would come into a fixed position that would be in line to support that small gauge. If it was a larger gauge, we would move to a different position. And then the moving actuator, which has a tool attached to it, can produce the actual angle that we form that bend to. So if you need to bend to 45 degrees, we would position to a certain extend position. If you need to go to a 60 degree, you could increase the distance that you're extending, so you would bend that angle slightly further. So in that approach, you can have one machine that can do a very large variety of different product SKUs, and you don't have to do significant tooling changeovers or tooling development or understanding, all of the spring back that is needed for a particular gauge size or particular temper. If you get a new batch in and the temper has a little bit more spring back, you can just update that recipe, go to a little slightly different servo position, and then run that batch and get the output quality that you need. If you look at more complicated, as you start going into radius bends or combinations of radius bends and angle bends, that's when you need to have, in many cases, product-specific tooling or recipe-specific tooling. And that recipe-specific tooling utilizes a female form and a male form tool, and we will generally bring those together to hard stops. And so, similar to the tip crimping, we'll come together to hard stops. It will be a very repeatable process. It will do the same thing every time, and the resulting geometry will be very consistent. It's not a disadvantage, but one of the considerations that you need to take into account when you're doing more complicated geometries, radius bends or combination radius angle bends, is it's a good idea to incorporate vision systems into the equipment where you're doing in-process inspection of certain aspects of that geometry. And that vision system will be able to track and measure the produced geometry at the next station, for example, downstream of the forming tool. And that will just ensure, and it provides another level of quality check, that the output product is meeting all the input requirements. It is common that tooling will go through a few iterations of development within our team. So when we first get a geometry that needs to be produced, we have a process that is able to create very quickly some soft tools to be able to form the number of samples. So we will create prototype tools, we'll form cannula, we'll inspect them, measure them, see if we're within the geometry requirements of the drawing. If we're not, maybe we have to make slight adjustments to the angle, to the radius, to the male form, to the female form in order to dial that into producing the final geometry. So typically that can happen in 1 to 2 iterations of that tool, from prototype to full hardened tool. But it is a consideration for the engineering effort that is needed for that level of geometry detail.